I want to thank all of you for coming to my talk. And I specifically want to thank Epic for actually inviting me. And one of the main reasons is I'm not an optics person, even though I work for a fiber photonics company. I'm a quantum technologies person. But we're trying to build a next generation of quantum technologies integrated inside hollow core fibers. And one of the applications that we're hoping to really explore is underwater communication and underwater navigation. In fact, we've recently won a Quantera, which is a European-wide funding to develop this technology. And we're here trying to look for partners to actually develop this technology. So I could just dive straight in. I think the main problem is GPS. The GPS is a cornerstone of everything in our society. It's allowed so many advancements. However, the immense value of GPS to the world economy is looking more like an over-reliance on a single vulnerable aging technology. Susceptible to solar activity, and more importantly, it's acceptable to jamming. With the recent war in Ukraine, we could see many instances of jamming or spoofing of GPS and GNSS signals. But most importantly, they don't work underwater. Now, we want to create another type of navigation system, which is based on a different sort of idea. Instead of using satellites and atomic clocks to be able to precisely determine your position underwater, we want to use magnetic fields. In particular, we want to use the natural magnetic fields that already exist in the Earth's atmospheric system. So this is a cartoon sort of drawing of the different parts of the Earth's atmospheric system. And there's a certain type of magnetic field which we all know about. This is a magnetic field that the traditional compass measures. This comes from a fluid and a solid core. And this is amazing in terms of what it allows us to do. However, it gives us the orientation of where we are on the Earth, but not the location. It gives us north and south. However, there's another magnetic field which is often overlooked. This is a magnetic field that comes from the lithosphere, the first tens of kilometers of the Earth right underneath us. Now, this is composed of many minerals which have been deposited via volcanic outflow. And this volcanic outflow has very specific spatial geometry, so unique that if you can measure the distribution of minerals right underneath your feet and compare it to a map, you can precisely know your position on the Earth. What's shown here, this is actually real data from the NASA probes that measure magnetic fields. These are just the magnetic fields coming from the lithosphere. And you can see the very interesting patterns which come about due to the unique configuration of minerals in the lithosphere. So if you can in principle measure these magnetic fields, you can actually know where you are on the planet without the need of any sort of satellite or atomic clock technology. Now, to give you an idea of why this hasn't been done before is here's a little graph about the different magnetic fields that come in the Earth atmospheric system and their magnetic field strength. What's plotted on the y-axis is the magnetic field strength, and on the x-axis, what we call the spherical harmonic degree, which is a relative idea of the spatial distribution and the uniqueness of the spatial distribution of the Earth. Now, the red ellipse is what's coming from the fluid core, solid core. That's what everyone knows, and it's the strongest magnetic field. You can see that all the different parts of the Earth's atmospheric condition creates a different magnetic field with a different spatial distribution. And the blue blob is a magnetic field that comes from the lithosphere. And there's a really nice range in terms of spatial distribution of magnetic fields where it does not overlap with any other source of magnetic fields. So if we can access this blue blob, we could create a system that could actually measure the spatial distribution of magnetic fields under your feet and use that for a new type of navigation system. But if you notice, these magnetic fields are weak, from a picotesla to the nanotesla. And more importantly, they're right next to the strong magnetic field of the Earth's core. It's 3 to 4 orders of magnitude larger. The most conventional magnetic field sensors just saturate at that point, even if they could measure these small fields. But more importantly, we don't want to just measure the magnetic fields. We need to measure the direction of the magnetic field to know precisely where we are. As a result, we turn to quantum technologies. Now, this is actually my lab that I built for my PhD. It's an ultra-cold atoms laboratory where we're able to take atoms, strontium, potassium, lithium, and cool them down to 1 nanokelvin temperatures. Because at these temperatures, we can create quantum states, entangled states that are very sensitive to magnetic fields. In fact, in this particular experiment, we could create magnetic field sensors with these cold atoms, which can measure sub-femtotesla, 100 attotesla magnetic fields, which is more precise than a single neuron at the center of the head in principle. In the inlet that you see over here, you can see the blue blob and the red blob. These are ultra cold atoms of strontium and lithium. that we're able to use to create these sort of magnetometers. These are amazing technologies, but they always stay in the lab. And the reason is these entangled states are very fragile and they need to be kept in large vacuum systems, as you can see over here. And these vacuum systems have for now been not miniaturizable. But with these systems, we're able to do amazing things. Now, I won't go over this that much unless you have really strong questions. But the most important thing is we could create a very particular type of quantum entangled state called the dark states. These dark states are extremely sensitive to magnetic fields. In this particular realization, we're able to get to 100 femtotesla or root hertz sensitivities, which is more than enough to measure the magnetic field of the Earth. However, for now, it has not been transportable. Our goal or aim with the project, with this EU project, is to compress the capabilities of these quantum optics laboratories inside a hollow core fiber and to create quantum sensors which can fit in the palm of your hand. We want to reduce the volume of these quantum sensors from meters cubed to hundreds of micrometers cubed. And we want to do that using a proprietary technology from GLOphotonics, which is where I'm based. And these are the hollow core fibers. So I think most of you know these, but just to do a brief introduction, instead of a solid glass core in which the light propagates, we have a hollow center, as you can see on the top left. We have this sort of a microstructure cladding array around this hollow core, which serves as the main means for light propagation. However, inside this hollow core, we can create a vacuum up to 10 to the minus 10 millibars, which is exactly what we need for quantum technologies. We can hermetically seal them. We can load it with atoms and create a very quiet environment for quantum optics. You can see the sizes and the different patterns of this. Actually, for this, we actually been awarded several sort of prizes for this technology. But now what we're able to do is we could actually take ultra cold atoms, or cold atoms. What you see here is the image of atoms at cooled out to 1 microkelvin temperature. And we could load these atoms inside this hollow core fiber. And with these temperature of atoms, we could create these quantum sensors, which can arrive at, in this particular case, picotesla level of sensitivity, but in the size of your hand. Just to give you an idea, we also go in the opposite direction. Instead of having cold atoms, microkelvin inside these fibers, we can have extremely hot atoms. In these particular cases, we can also load plasmas up to 1,000 Kelvin inside these fibers itself, if this interests anyone for application. What our hope is to create a novel quantum sensing architecture, which can incorporate all cold atoms, quantum states of light, optical coatings, but also all of the elements that we need, for example, magnetic field inductions, magnetic fields, and all the electronics inside a handheld package to measure magnetic fields, not only their strength, but also their direction. Now, we want to use this for a new form of navigation system. Now, the standards for navigation systems for underwater, for submarine and underwater, is, well, in general, standard navigation is GPS. However, the GPS does not propagate underwater. It's susceptible to solar activities, and it's susceptible to jamming by adversaries. When we go to underwater, especially submarine navigation, we go into inertial navigation systems. This is actually something I've worked at before. We used to take these ultra cold atoms, nanokelvin temperatures, and we would create atom interferometers. So it's an optical interferometer, but we use the wave-like nature of atoms to be able to create the interferometer. And with these, we could create very sensitive accelerometers. The moment you go underwater and GPS fails, you can measure your acceleration. And from the acceleration, you can know where you are. However, these are very complex and expensive. They're not compact. They have large measurement drifts and they have low update rates. And underwater, of course, there are a lot of other really interesting and very niche applications, which are really interesting. For example, acoustic positioning systems, which try to create a type of GPS underwater with acoustic systems. However, these are not quiet, they're not available globally, and they require infrastructure. We envision a system that, first of all, can give absolute accuracy up to, for right now, we're planning on 100 meters precision, but hopefully we're hoping on better. We want something that's unjammable. This is mainly unjammable because the magnetic field signal comes from kilometers of lithosphere, the Earth underneath us. So it's almost impossible to be able to disrupt this magnetic field by an adversary. We want large update rates because if we want a ship that's traveling, we want it to be able to take larger than 10 data points per second. We want something that doesn't require infrastructure that's global and it's passive. And just to give you an idea of who we are a French startup based in Limoges, France, which is mainly known for porcelain. We're mainly an R&D company focusing on deep tech. We have about 20 employees, most of them PhDs. We have our own fiber drawing towers and our own cleaning rooms. And we have really strategic partnerships with academic institutions from around the world. And we hope to kind of continue these partnerships, not only with academics, but also other companies. So if there's anyone that's interested in these magnetic sensors for underwater navigation, but also for seabed mapping, we would really like to get in contact. Anyway, thank you so much. And if you have any questions, just let me know.